Hi, I wanted to talk to you about force of buoyancy and principle, Archimedes' principle of buoyancy. Principle simply states that when an object is in contact with a fluid, and because of this contact, it has displaced some fluid out of the way, then if you look at the weight of that fluid that got displaced, there will be a force of buoyancy on the object. We call it buoyancy force, okay, upward. So here is an example that may help. So if I have some support, and here is a string, and there is a block. That block has a mass m. So right now, if this is the case, right now if you look at the forces in the block, what you're going to have is weight of the block and the tension force in the string. So if we look at the tension will simply be mg, since the acceleration is 0, right? So this all. Now let's see, we bring a fluid while the block is hanging there, and say same block but maybe quarter of the volume. So this much part of the fluid is no longer there. There is block now, and so that has been displaced. So this corresponds to what we will call displaced volume. So this volume is displaced fluid. So that's the volume of the fluid. So right now, when we look at this now, the block force in the block, you have mg, same as before, but in addition to mg, let's call this tension in this case tension prime. Let's call it prime, just in case it's different, okay? So I don't want to get confused with the old symbol here. So maybe magnitude may be different. So those two forces are still there, but Archimedes' principle says that in addition to this, because there's a displaced fluid, there's going to be a force from the fluid upward, which means there is another force. We call it force of buoyancy. So this force of buoyancy. So there will be now three forces. And if you say what's the acceleration of the block is 0, so the formula now will be the tension now plus Fb minus mg equal to 0. So tension is actually less now. Tension prime is mg minus force of buoyancy. So say an example will be maybe this is a quarter of this. So this height is h, and this area, if let's assume this like a simple cubic volume. So the displaced fluid is actually a shape of a parallelepiped, where height is h and the area is a. So the volume will be 8 times h. So we want this Fb is the weight of this fluid. So I need to multiply this volume with the density of the fluid. We use the letter rho for that. So the mass of the displaced fluid is simply rho times A times H. This is the volume and this is the density. So it's the weight of the displaced fluid will be this times G. M displaced fluid times G. So if I write this whole thing out, rho A H G. So this is H is the not the height of the whole cube, but just so this will be T prime equal M G rho A times H times G. So we have a this is an application of that. Let's look at a say this is a ship, and maybe that much is underwater. So this is say water, and so actually the area, this thing is very complicated shape. You can see that if the mass of the ship is not, it's just the hull itself and whatever inside is contained, so all of that is mass m. And this is not simply saying how much this height is, but we say what's the volume volume that's been displaced is kind of this shape. So the volume of this shape, and maybe hard to compute, but maybe let's see that's the volume displaced. We just use this for that part, not the entire ship. The volume of the entire ship may be volume of the entire ship is all, and this is volume under, right? And that's what that's displaced. So here, once again, it's going to be very, very simple that at this point in time, this mass, there's one force on the ship, and then there is a force of buoyancy on the ship that they must be cancelling because there's no acceleration of the ship, vertical acceleration, I mean. So we get volume under times the density of water times G, so that's the force of buoyancy, which is up, minus mass of everything that's in the ship times G equal to 0. So if I know volume under water, volume under times density of water, that can give me the mass of this ship. Let's look at an example application of buoyancy. Suppose you're given an irregularly shaped object, for instance, a crown, a rock, some piece of metal, that's the volume is not easy to get. If you have a cube shape, for instance, you don't need this, right? When you have material of shape, nice shape, you can find the volume, you can weight, get the mass, and then you get the density. But what if it's the material does not have a nice shape? You can still try to get the volume from doing displacement method for the, to get some other method about volume. But suppose we don't have those methods, or we don't want to do it that way. We want to use buoyancy to find out the density. So there are a couple of steps. These steps can be done in a lab. So the way we do it is we try to wade air. Okay, so you can have a balance, and you can hang it here, and so this is the pivot, okay? And so this side, you can adjust the weight and tells you how much tension is here. So this tension is what we are measuring when you're hanging something. So this method is that way. So this some kind of this is balance, and you put some weights here to balance on the other side, and that weight. So this guy is a reflection of the tension pull, right? And that's a reflection of this weight. So that say I got W doing that. Okay. Now how do we do this? The next step is to actually look for a fluid in which this thing will sink. Meaning the density of this thing is more than the density of fluid. So if this thing is floating in, say you have a fluid water, it's floating, it's not going to work. This method is not going to work. Then you may go get acetone or get some other lower density ether or something. You can get a lower density fluid in which it will sink. Okay, so you just find a fluid to sink, and let the density of the fluid be rho sub f. So this I'm going to call a density rho, which I do not know. That's the one I need to find, right? We are trying to figure out a method to find that. So this is air, but this thing we want to measure how much it's going to weigh when it's fully submerged. Well, what do I mean? Well, we will have some kind of container, say a beaker or something in lab, and you can have enough fluid so that this whole thing is submerged. Now you're going to have an upward force of buoyancy, and so this tension will be now different, and this is what we are calling W prime. So this is now less than before, because if you look at the free body diagram now, for this guy you have this, which we're going to call it W prime, and then you have the original weight, you have a W, but on top of that you have a buoyancy going up. So in this experiment, step number 2, my experiment looked like W prime minus plus FB minus W equal to 0. So we measured this and this. We didn't. We can actually get FB from this, but how do I get the density? So this is. So we need to look more closely. So I'm going to rearrange this and figure out what this FB's formula is. So FB by itself, the formula here is, so the volume of this thing, so it has some volume V, and the entire volume is displaced. That's why the fully submerged was necessary. Okay, I want all the volume, and we don't have a clue how to get the volume correctly. Okay, so I don't want to have an experiment in which I'm forced to find the volume. So I'm trying to figure out, can I have a way of canceling the volume from my calculations? And turns out yes. So this FB is simply going to be the volume that was submerged, which is fully submerged, the density of fluid. So this is going to be mass and then G. So it's the weight of the displaced fluid, right? So that's the FB. And if you look at W, W itself is pretty similar to that. Volume, same volume, rho I want, and G. So I'm after this quantity. So let's write this over here with FB on the other side. So this one looks like W prime minus W. These are the things I measured, is equal to W prime plus FB. Yeah, so this will be negative. So let's write it as a positive number. W minus W prime equals FB. So that now everything is positive. basically what I did was W take there, W prime take there. So that's written like that. I see the V is in here and V is in here. So if I were to divide both sides by W, so these are measured quantities. I see the volume will cancel out from here. So the FB just, this is just rho F over rho. FB was V rho F G, V rho G. So V cancel, G cancel. So the right side just get this. So this equal to that. Now we have this ratio in terms of everything that I have measured, right? So I can write the inverse of this. So rho over rho F, so this equal to that guy, inverted. W over W minus W prime. And I can send this on the other side. So my final answer will be rho of my stuff, W over W minus W prime times rho of the fluid. From all, I know the fluid's density, I know how much it weighs in air, my material weighs in air, and how much is it weighs when it's fully submerged. So say I have an example. Suppose something, the fluid is, say, alcohol of density 0.8 gram per centimeter cube. Suppose I have something like that. And the weight in air was 500 grams. Say mass in air. Mass in air was 500 grams, which is weight over G written in these units. And mass prime was say 450 grams, which is W prime over G. So I wrote them down consistently. Now you can see that the G will all cancel from here. So this can be mass in air. So you can actually use this in the units that are provided here, because I don't need to convert any of those things. I don't need to multiply by G, etc., convert gram into kilogram, etc. Because of these ratios. Now, when I put these things in there, rho will be mass in air, which is 500, mass in air 500, minus 450. So gram will cancel with gram, so I don't need to even write that. And this will be 0.8 gram per centimeter cube. So I don't need to convert any unit. This is the beauty of it. So I have 500 divided by 50. That's going to be 10. So this is actually 8.0 gram per centimeter cube. So this is the density, can be density of steel, for instance. Okay. All right, I'm going to stop here. This is, but before I really stop this video, I want to emphasize that this is a good experiment. If you wanted to, if you have a spring balance or something like that handy, you don't need to that. You can just have a spring balance, and spring balance will tell you the weight or apparent weight, and you can try doing this experiment at home. Hopefully you get some intuition when you do actual experiments. Okay, take care, bye.